Welcome all to the 7th edition of the Geoscience and Remote Sensing Society Young Professionals and International Society of Photogrammetry and Remote Sensing Student Consortium's Summer School. Well, this year we will be offering webinars, roundtables, and tutorials with hands-on like this one today. And this edition is organized by two Santa Catarina State universities in Brazil. It has the strong support of two scientific societies, the Geoscience and Remote Sensing Society and the International Society of Photogrammetry and Remote Sensing, and their student branch. For the first one, the young professionals, and for the second one, the student consortium. We welcome all to visit our main webpage and also to take part of the quiz of Santa Catarina State and some particularities of the south part of the country, and to also watch the welcome words of our rectors and presidents and chairs of the scientific societies mentioned before. This event has the strong support of our state foundation, FAPESC, and two companies, Canoinhas Geoassessoria and Instituto Gilto Volpato de Educação Científica, that provided a strong support to our event. The event has also been promoted by different Brazilian institutions, and we offered already some webinars, two roundtables, and tutorials like this one today. I will be inviting now Professor Raul Feitosa, that is a professor from PUC Rio, to give the welcome words to everyone. Raul, feel free now to give your
Thank you. Thank you,
thought.
Veraldo, for the introduction. I welcome everybody. Good morning, good afternoon, good night. I don't know exactly who you are, where you are. This is the second part of our tutorial on Google Earth Engine, being conducted by Dr. Ricardo Dallagnol. In the first part, held last week, Dr. Ricardo Dallagnol presented the GEE basics. In today's section, we are going to learn how to run deep learning algorithms within GEE. Regarding our speaker, I also already introduced him last week, but for those who are attending, who did not attend the last week section, I will say a few words about Dr. Ricardo's experience. Dr. Ricardo is environmental engineer, and he did his PhD in 2020 in remote sensing in the National Institute of Space Research, known as INPE in Brazil. He currently works as a researcher at INPE's Earth Observation and Geoinformation Division. He has experience with several applications in the area of biogeosciences, with focus on tropical ecology, nature conservation, and environmental monitoring in Amazon rainforest. He works in quantitative research using advanced data types such as high-resolution satellites, optical, and airborne LiDAR data, as well as methods such as deep learning convolutional neural networks. This is exactly the topic covered today. So his current project is to study large-scale pattern in the structure of the Amazon forest, which is a hot topic here in Brazil. I think it's important for all the world, and he aims at understanding processes of tree mortality and forest degradation. So we welcome Dr. Ricardo Dallagnol. It's a real pleasure to have you here today, and we are looking forward to your talk. So you may take control, Geraldo, if it's okay for you.
Yeah, let me just introduce also Daniel Augusto da Silva. He is a PhD student at the Regional University of Blumenau, Furby, and also working on tropical forest and mapping procedures and all this for the Mata Atlântica biome. So, yeah, Ricardo, feel free actually to start. And in the name of the Brazilian chapter of the Geoscience Remote Sensing Society, we also want to acknowledge actually for your availability. It was actually planned for a small group of students at PUC Rio, and thanks Professor Feitosa, he make possible that we could offer it also in our event as a tutorial. And I think that students and also young professionals can really benefit actually from this course, and given the large actually audience in several countries, I think this is really a good perspective and possibilities actually of applications. And in the end, we may also to make a short actually roundtable to discuss actually a bit of the possibilities and forthcoming perspective for research and applications. I think this is great and wonderful. And again, actually, thank you a lot actually for your availability and disposal actually to offer this tutorial. Thank you.
Yeah, thank you, Veraldo, both you and Raul for the invitation, and also all the organization to make this possible. Um, as Raul was saying, last week we talked about Google Earth Engine, how to extract data from Google Earth Engine, how that allows us to run models such as machine learning, deep learning models in our computers. And today, for this second part, I will be teaching you something about deep learning applied for remote sensing. Um, this is more directed to people that like to give a brief introduction on deep learning for remote sensing. So who doesn't know anything about deep learning will get a brief introduction. Who already knows about deep learning, such as the students from Raul, from PUC Rio, but they don't have much experience with remote sensing, they will get a grasp of how to deal with the imagery, how to process, how to arrange the image to apply the models. So I will first let me share my screen here. Entire screen. Share. Can you see my whole screen?
Yes,
Okay,
perfect.
great. Um, this is the topic of today's lesson, and I start by actually apologizing for some of the code that I provide on the GitHub. That the organization could paste the GitHub link on the chat, please. Some of the code of the GitHub that we will do it today together on the Google Colab platform, it's actually not working. I tested it last month. It worked perfectly on a workshop that I gave on this topic, but I tested this week and it was not working. So this part that we will not be able to do it together, it's a bit sad because it is the same example I'll show you with R in my local machine. But I prepared another example with, it's not satellite imagery, but the MNIST data set we'll see during the course today. I'll start by giving you a short lecture on the basics of the deep learning, and then we move on to some exercises, and it will be a little less practical than last week, so I apologize for that. But I think you learn some interesting stuff. So I expect that for this lecture, that by the end of it, you are able to describe what is deep learning, explain the innovation brought by convolutional neural networks, the CNNs, to identify the main steps on applying a CNN with remote sensing imagery, and lastly, to apply an example of CNN with a test data set. And this will be the MNIST data set on the Google Colab platform. And I will show you the example that I told you. Unfortunately, it's not working on Colab, but I'll show you on my local computer. All the data is available on a repository that we'll send you the link in a while for the it's also in the GitHub link. You can run on your local machine. I will show you how to do it. Just a second here. I forgot to turn on my thing here. See if it's working. Okay. So let's go. First thing is that artificial intelligence, AI, is the new electricity. This is not my quote, but it's from Andrew Ng, one of the masters of deep learning. You can search his name, Andrew Ng. You find many tutorials on the internet, on Coursera and other platforms. So Andrew is like a beast of artificial intelligence. You should. I once did a course on how to code the basic neural network thing with him. Like he's a very good teacher, much better than I. And here I showed you just some examples of how the artificial intelligence is present on our day-to-day life, like on Facebook, on games, on Google Translate, on finding objects in an image, on robot perception, on these self driving cars that people are building nowadays. So it's present on our day-to-day lives. And so it's something that's it's like shaping the markets. It's something that's revolutionizing how we live today. And now more regarding to remote sensing and images on computer vision. So that's how to make computer uh, look at things. We have basically four types of activities that we do with images. The first one being the image classification, that the task is to say what is present on this image. So like a person, tree, grass, the sky. So the task here is to just label like what's inside this image, and you can teach the computer how to do that. A second task is for object detection. So the task here is to create these boxes encompassing the objects that we want to detect, to identify. So these bounding boxes, which are these rectangles usually called, are the output of an object detection model. This is the second task. The third task is the most common type of classification that we call in remote sensing terminology, the semantic segmentation, which the objective here is to map with a single value each type of object that we have on an image. For example, we have a person here, so we put a value of, let's say, 1, and here is like all red. We have vegetation or trees, we put a different value here. We have like the sky, so we put a different color, different number here. We have the grass, so we put a different number here. So this is semantic segmentation. This is what we call in remote sensing the image classification. But in this terminology that I would say deep learning is like putting forward, because we have all these different possibilities. Uh, this is indeed called semantic segmentation. And the fourth one is the instance segmentation, which is very similar to semantic segmentation, but the goal now is to identify for a given object, a given target, for example, persons on this image, different IDs, different persons. For example, this is person 1, this is person 2, 3, 4. So imagine this is a satellite imagery. We want to identify different uh, crop fields. This is crop field 1, crop field 2, crop field 3, or different houses on a city, on an urban environment. So this is what instant segmentation does. It's the most high level thing we would have right now with this type of applications. But usually we work with semantic segmentation on the remote sensing world, which is very nice. Uh, but newer models are walking towards the instant segmentation. And here I show you 2 examples that me and my group worked with. Here's a paper that Fabian Wagner led. We were interested in mapping palm trees. So this type of thing here, let me put another color here. This type of thing here, the palm trees. So they have this distinct uh, like star shape on the canopy, forest canopy, and we were interested on mapping these species on the forest. So we hand delineated lots and lots of palm trees in the canopy, and we taught the model how to map this at a large scale. So imagine this is a very small subset with let's see, 40, 80, 120 meters. So 120 meters here and 120 meters here. And now here on the top we have 10 meters just on this scale. So it's about more than 100 perhaps here. So we can map these things on a very large scale and look at patterns such as this related to topography, such as patterns related to the rivers or to human presence nearby the rivers. We can study this kind of stuff on a large scale. So here's a very nice application of deep learning, uh, very innovative. And one interesting thing that we are learning about the deep learning methods that often false positives are very often true positives. So sometimes the model map targets that we were not able to see. So the model is actually surpassing our ability to find the objects, and we have to redraw the data sets, improve the data sets because the models are too good. So they achieve human level of detection, visual interpretation, and sometimes even better than we do. So this is actually a challenge for us to how to train these models. And a second example is on instance segmentation focused on a urban environment, that the task was to map different houses, but not only map like this is, oh, sorry, let me get a different color. Like this is uh, buildings, like this is buildings. We want to see this is building 1, this is building 2, building 3, build 4. So different buildings. And with this data set, uh, Fabian Wagner also showed that we were able to do that. And when we look again at the large scale, it's awesome to look at different houses, different buildings, and this can be quite useful for uh, urban planning, for the organizations that we deal with counting how many people are living, where are the sectors of the city that is growing, so we can plan it better. And going back a bit, we see the deep learning as one specific area within the artificial intelligence. So we have artificial intelligence, machine learning, then I added a little circle there for the artificial neural networks, and then we have the deep learning. And why did I add this thing here? Because we have some uh, neural networks that are not very deep, so they do not have the deep on the deep learning, like very present. Like for example, a multi-layer perceptron model, which is this one, which has only the input layer, output layer, and on the middle here, we have the neurons, these units here that like do the processing. So we have only one uh, layer, one hidden layer. And when we talk about deep learning, deep neural networks, we should have many of these layers. Like here's an example with 3 layers, but we may have like dozens of layers, hundreds of layers, and with lots and lots and hundreds of neurons with millions of parameters instead of just like a few hundreds of parameters like in this model. So this is a difference between this non-deep and the deep neural networks. And going back just a bit more before we proceed is a basic concept about neural networks, very simplified. The goal of a neural network is to approximate a mathematical function. So to relate some input, let's say X, we have 3 inputs here, like imagine these are 3 different bands from a satellite imagery. Um, and we want to estimate the y, and this y could be like a value for, let's say, crop biomass or forest biomass, or could be classes. Let's say the y could have a value of uh, class 1, 2, or 3. This is not exactly how we do this here, but we could have the classes here as well. And this is just one neuron, like the most simple one. And the thing that happens here is that the neurons, they relate the inputs with the neurons and then the output. So what's if we between the inputs and the neurons here are the weights. So these weights are where the magic's happening, where the model is being constructed. So these weights, 1, 2, 3, for example, is where the model learns these weights and is able to uh, make this relationship work. So imagine this is like a regression, so that you have x times w1 equals y. So you have this combined x's and w's and to make the y. And talking more about a timeline, we have the first perception thing is around here. Then we have the CNNs, the most advanced methods, around here. So from 1958 to today, well, there's a lot of time, like 70 years, but uh, this is now like, if the evolution was like, okay, we are evolving a bit, this is now like this, like we are just skyrocketing the number of applications and number of things we can do with deep learning. And this is probably motivated by the hardware. We have much better hardware nowadays, and so we can have these more robust models. And the MLP model that I said before, it was here 86. We have like another models like in 97 the LSTMs, which are for time series applications. but we end up with the CNNs here on the end, which is the core of what we are looking today. So from the more advanced models, more recent models that we have nowadays, this is like a summary of the available traditional models. Let's say you can see that the CNNs are located here at the 2. Um, we also have so this is the main thing for the class today, but we also have different types of models that are very interesting as well, like recurrent neural networks that are good for time series. The encoder decoder architecture is also thing we are seeing today. The auto encoder is a very nice method for unsupervised classification. The generative adversarial networks is the thing we see like on the Facebook that is like the deep fakes, like changing faces of people. There are some applications for remote sensing for this as well, um, like correcting correcting imagery. Imagine we have a very noisy image with lots of noise, and we if we can learn how to represent this, we can make this like a noiseless image. So this is something that the generative adversarial networks can do for us as well. And this last one, to be honest, I didn't go into it. You are free to take a look. But we'll talk mostly about the convolutional neural networks and the encoder decoder today. Um, we already talked a bit about the perceptron, so just reinforcing here, it's basically an equation that relates the output with the input through weights. So something like this, but more complex, okay? And how does the model get these weights? By doing the learning. And this learning, let me see if I put okay, I put a small cartoon here to represent. We train these neurons like to represent like the brain. We train these neurons by saying, let's say we start with random weights, and then what we expect to get from the y, like a bad result. But how bad is it? Like you get this y, but in relation to the y that we expect, like let's say it's ye, how far is it from the goal? Like let's say if the y is bigger than what we expected, then perhaps we should uh, reduce the y. Then um, or maybe and to reduce that we should change the weights. So there are several algorithms, models to make the neural networks learn. One of them is called backpropagation. So the simplest way to put that is it propagates the error back to the network. So splitting the error that we have on our y estimate back to each of the weights. So put on a simple way, this is what happens inside each of these models. And so we can get a grasp of what's happening with this model. We have this visual aid brought by this website. We are now going to open this website. I asked for the organization to place this link in the chat, or you can also memorize it, playground.tensorflow.org here, and go to your browser. So this this thing is it's like a neural network built in this website, and you can play with it. So I'm just gonna show you 2 examples here, and then you can play a bit more with it. So basically, remember we have, like, for example, two inputs. So these are just two images with different values, like on the horizontal or horizontal or vertical axis. We have like 4 neurons on the hidden layer, and we have an output of, let's say, just 1 neuron. And we want to predict this point here, the blue and orange ones. So when we click on the run pause here, we ask the model, the network, to learn these patterns based on based on these two axes, to estimate this point. So we put play here, and it quickly learns this pattern, splitting the two classes of blue and orange points. So this is a very simple task because they are very well split between the image. But let's test. Perhaps we have less neurons on the hidden layer, and we have these two inputs. We had this just two neurons. Let's see what happens. With two neurons, the networks didn't do a very good job. With it achieved a 28% error on the estimates, because lots of points of the orange are in the blue area. Um, so it didn't achieve a good result with only two neurons. When we added like three, let's say, perhaps three works already. Three still don't work very well. When we add four, that is the original, it's able to model, to achieve that representation very well and achieve a error close to zero. We have here on the left other examples, like other examples. Imagine this is two groups. Like what do you do here? Just split in the middle, 100% accuracy. Like this is an easy one. But now we go for a more difficult one. How do we split this based on only these two inputs? This is a more difficult job. Let's test with the previous model. It didn't achieve a very good job, like almost 50% error. Like it's just splitting them in half. Now it's still learning. Oh, it's improving a bit. 45. So it iterates through. It learns with time. So it's still learning. 42%. But this is probably what it's going to stop. It's not going forward much better here. And then you can change like the learning rate, how fast these neurons they learn. So and you can change the number of hidden layers. For example, let's say we put 3 hidden layers with 4 neurons as well. So let's see what happens now. To be honest, I don't remember what's the minimum network to make this work. You can play and try to find it. This one, okay, it's improving. 48, 47, 46. But I'm not very confident that this will work. Like the blue area is still here. Let's just make a more big network here. Let's add some new inputs here, just in case you have these new parameters, and let's see what happens. So the model is now going crazy, trying to model that that output. It achieved 18% of error. Still flickering, trying to adjust the weights. So one important thing here is when you look at these neurons, each of these neurons have a representation of the inputs. For example, this neuron have this representation, this neuron have this representation, and so on. So each of these neurons, they learn how to represent the data on a different way, which is similar to if you study like a principal component analysis, a PCA, that extract features from the data and represent it on a different way. Yeah, that's the simplest way of explaining this. So these neurons are trying to do that as well. So each neuron learns how to represent this data on a different way, and in the end we have this output which not very good, achieve an error of 18%. But when we look to this, we say, okay, it got a 19% error, but lots of these areas are very bad. Imagine we have points around here. If they are blue, okay, but if they're orange, they're bad. It's kind of hard to interpret what's going on inside a neural network. This is simply put one of the lessons that we get from here. It can do a very good job, but it's usually hard to understand. So other concepts that we get here are the epochs, which are the number of iterations that the model is learning. We have the learning rate, which is how fast the weights are being updated. So it's basically like if this is 3, it's like 3% of the error is distributed back to the network. And we have other more advanced things here. I will not speak now, but you're free to try and do a better result than me on this example. Okay. So going past this basic neural network model, we now enter on the deep learning, and just a comparison. In the past, we had like multi-layer perceptrons, for example, which are now implemented in lots of machine learning packages in R and Python and everywhere. But just 10 to 15 years ago, even multi-layer perceptrons were not very easy to apply. Like you'd have like MATLAB with a neural network method implemented, but it was not easy to apply this. Nowadays, you just run one line and you run a multi-layer perceptron. They usually have or had a very low number of layers, like usually less than 5, and it had a similar accuracy to traditional machine learning algorithms, like random forest, for example. The random forest can achieve a very similar result to a multi-layer perceptron. And the domain of the analysis is still the pixel level or regional. So imagine you have like an image here and you have the pixels. The models would learn to predict for each pixel. It will learn the what a single pixel is representing and predicting. But now, from like 5 years ago and today, it's much more present. We have the convolutional neural networks. They have much more layers, like 20 layers or even more. They have more advanced ways to understand the images that I will explain in a while, and they obtain above the traditional machine learning accuracy, like much better, much better. And they work on a patch level. So this is a very important concept. Imagine here you have an image. Now, it will not work as a single pixel at a time. Let's say this is a pixel, but it will work usually with patches of images. Like this is the patch. So instead of looking only one pixel at a time, it looks to a group of pixels, a window of pixels, which are called different ways in the literature, like patches or chips or tiles. I usually use patch. In this lecture, I use patch to represent these different areas of the image that we are looking for. So the model, instead of looking to one pixel at a time, it looks at patches. So pixels are here. Okay. So this is a very important concept. And from the convolutional neural networks, one very interesting architecture that my group is using is the UNet, which is this kind of stuff here you're looking. If you split in the middle, you have a different network, but I'll just explain the UNet here. The UNet now, instead of that simple representation of neurons or input, the neurons and the output. Let's say 2 neurons here, and the output, oh, let's say this is the output. Instead of just doing this simple representation here, like a multi-layer perceptron, for example, just a neural simple network, we have now this thing on the left. And what this does is, on the first part of the model, it learns how to represent the image on different scales. So it goes from 128 by 128 image to 64. And while doing so, it learns the context of the information. So not just looking for one pixel, but looks to the context. And it proceeds to reduce the size of the image more and more until it achieves just a vector. Like the image is like the features are compressed into a single vector. So the image is now like represented by this vector of 1024 values. So before we had 128 by 128 values in this image, and now we only have 1,000 values. And on this second part, which is uh, uh, the up convolution, we now go back to the scale of the original image, and now we find these the segments that we are interested into. So this again is only to say that input to the network is an image and not a pixel anymore. So this is one of the main differences in these models. And so this is the kind of model that we applied in this work, for example. Um, and if you can see in the image a target, if you can see a target in the image, the deep learning model can likely map it. So this is like a thing that we have around here. Like you can see this palm here, the model will probably be able to map it if you have enough samples to train it. And how does it learn? How does it do that very well? Second. So one of the improvements of these models over the past models is the use of the convolution. And the convolution is a basic mathematical operation, so it's not not a very fancy thing. Basically, you have a small window here that slides through your image, applying, for example, a filter, or in this case, we are going to learn the filter. So, and we also have, so this is the convolution, and we also have this operation which is called the pooling, which we reduce the dimension of the data to a lower dimension. Let's say we had like 1 2 3 4 5 6 7 8 9 10 10 by 10 image here, and now we have three like 5 by 5 here. So we reduce the dimension of the image by just getting the most important information out. So let's say for these regions here, these were the most important information. When we translate that with the pooling operation, we get this. And if we do the convolution again, the pooling again, we get a more even simpler representation. And that's what occurs in this part here, this process. But thing about the convolution, you can do a convolution with a simple filter, like this filter finds the horizontal patterns, this filter finds the vertical patterns. So you get this. So you get all the horizontals, you get all the verticals. If you combine these two things, you get, for example, this robot represented here. But the thing is, but if you don't know which filters you should use and which features of the image, like which bands are important, so what the convolutional layers, so these things here, what they do is to learn the filters. So we don't specify the filters. the network, it learns the filters. So this is the beauty of these models. They learn the filters. So they learn how to represent the texture of this image, the context of this image. So it's the same thing when you look at this image and you see like it's all like there's a texture because of the forest canopy. This is what the model will also see, something like that, instead of just one pixel that has a very high near infrared because it's a vegetation and something like that. It sees the context. So that's what the convolutional layers do for us. Uh, and here to the right is a representation of what this means inside. By looking at the context, it's able to find features of this cat, like the lines that represent the ears, the the eyes or the eyebrows or something like that. And when we merge these features on a next layer, let's say, it makes like a whole eye, a whole ear. And if this image here, it has this kind of eye, this kind of nose, this kind of ear, perhaps it's a cat and not a dog. So this is what the models do inside. um, and now we have an example with the MNIST dataset. So here's just a visual representation, but we will do in the code right now. um, what we want with this data set. This data set is like lots of numbers, like written manually. So we have these images of numbers, and when you look to these numbers, you obviously you can see, oh, this is a 1, this is a 2, this is a 3, this is a 4. But how to teach the model to do that? If you look just to the position of the pixels, like one value have pixels around here in these locations, perhaps you are able to train a model to detect this number 1. But what if I write this number 1 like this, like skewed? Perhaps the model is not able to learn that. But if we train a very robust model with convolutional layers, it should be able to map this correctly. And in the end, what we want with this kind of model is it's not an image, it's just an output from 0 to 9, which is this thing, saying this is a 0 or 8 or 9. In this case, it was a 4. So in the 4 here, it was all white here because it activated that part of the network. And now we go to the repository, to the GitHub, where we'll see the link to the MNIST example. So if you're not yet here, so please go to the GitHub and find this here, and then we click on Open in Colab. So I'll give you a second for this. Do we have any questions so far, organization? So it seems not.
No.
So I clicked on Open Colab.
Hello, Ricardo, can you hear me?
Yes, I'll go on.
Yeah, there is a question coming from Daniel Moraes. A question regarding the patch approach used in deep learning.
Okay.
How does the training data collection works in this case? Instead of collecting single pixels, how should we collect training data? Is it clear?
Yes. I will show you later on with the code how to do it, but basically what we do is we have the image here. This is like the whole image. Imagine this is a very big image, let's say 100 kilometers. And let's say we have mapped with, we know about some areas, like this is the feature I want to map, this is the feature I want to map, this is the feature I want to map. I don't know what are these. Maybe are crop fields, or these are forests, or these are tree species. Doesn't matter. But these are the true the reference. Um, so let's look a zoom to this thing here, like here. So we have this area here. Let's say this is a bit smaller. Let's say 1 kilometer. What we do is we crop the image with a grid, and then we get each of these patches to train the model. So instead of getting the individual values from inside this thing here, from the blue thing, like you get the pixel, this pixel, or this pixel, or this pixel, you don't get that. You get this whole patch here. So this is like the patch 1, this is the patch 2, 3, and in in this case, all of these patches, they contain the class, the presence of the class you are interested, but some of them also contain the the absence of the class, which is very important. We want to train the model to detect both the presence and the absence, otherwise it won't work. So it's important to have both the presence, the absence, and the presence on the same patch. So basically, crop lots of these patches, and we'll have like a folder in your Windows computer with lots of these patch images, and that goes into the model. I'll show you in a bit how does that look in the computer. Okay. Anything else? How?
No, I think that's all for now.
Okay. So going to the MNIST dataset, so opening Colab here, we want to make sure we are running a GPU environment. So let's just a second. How do I? Oh, see in English. Okay, now it's in English. We want to make sure we are using a GPU runtime. So in runtime, you click on change runtime type and click on the GPU. So if it's not GPU here already, you choose GPU here because it's faster than CPU. I will explain it later. But just find the GPU. So runtime, change runtime type, and GPU. Then you click on connect on the upper right. Should have a connect here. It will initialize your Google Colab session. When it shows this thing here, it should be ready. It's important when you place your pointer over this area, it shows like it has the GPU activated, like there is a small GPU written right there, you can see. And what's this data set? I got this from an example from MIT. This uses the MNIST data set, those numbers. We'll just run the first part. So if you're new to Colab, just click on this list on the left on table of contest here. So you see a list of what's inside, and you click on part 0. So we want to run the part 0. So you just click on this play button, the run cell, which will tell you this notebook was not altered by Google. Okay, just trust me, it's all good. Run anyway. This first part 0, it prepares the model, and while you do that, I will say this is not R, this is Python. I had a script for Colab in R, which was this number 3, with an example that I will show you afterwards. But the Colab changed something in October, and it's not running right now. So I'm sorry for that. So we'll run this example with MNIST. So in Python. So we run this part 0, then we move to part 2, which is the image segmentation example. You can also run the part 1 afterwards. I didn't even test it. It's a more like a regression problem, but we want to do the classification problem. So you run this first part here, set common constants. Uh, it will explain what's the input, what's the neural network doing. It's predicting the number. I already told you that. An important thing here is that these images from MNIST, they are 28 by 28 pixels. So each image has 28 by 28 pixels. So this is the whole image. In remote sensing, we have a much bigger image, so keep in mind that. And we have 70,000 of these images to train the model. So in this next part here, we assign, we actually download the dataset from Keras, and we assign part of that to train and part to test. So if I remember correctly, there are 60,000 for train and 10,000 for testing. On this next part here, it define a basic pre-processing of the image. It divides by 255 to normalize it between 0 and 1. On this next part here, it plots to show you what's the input. So it's important to for every step you do to check, like we call this a sanity check, to check what we're dealing with. So we're not blind in the process. So these are the inputs: a train image and a train label. Like this is a 50419. So these are the inputs that the network is seeing. And now comes the model. This is a convolutional neural network. Uh, you can run this part, and I will explain in a second. Why does this stay? Okay. You can run this block of the build model and this summary, the next part. So what is this part doing? It's not training the network yet. It's just defining the architecture. So because in deep learning, you have several traditional architectures. You'll see names such as VGG, ResNet, UNet. There are several, LeNet. There are several of these famous architectures made from Facebook, from Google. But you can make your own architecture with deep learning and adapt that network for the problem you're facing. Of course, you can use the famous ones, and they should work decently on your problem, but you can shape it, you can improve it, tailor your architecture for the best, to get the best results. This is the code, and this is the representation of what's inside the summary. So what we have here is a convolutional layer, conv2D, another convolutional layer, conv2D. We have a max pooling layer. Then we have a dropout layer, a flattened layer, and a dense layer, another dropout layer, another dense layer. So what this do? So if you remember correctly, the convolutional layers are those that we have the image and we have like a filter, and this filter will convolute across the image, and these, imagine that inside this filter we have like weights like W1, W2, W3. So what happens here is these filters will adapt, will learn, the model will teach, you will learn these filters. So here we have 32 of these filters of these small windows. On the second layer, we have 64, so bigger number of filters. Then we do the max pooling. So the size of the filter is defined here, a kernel size of 3 by 3. So this is the size of our little filter, 3 by 3. You can use a different size, but 3 by 3 is the most used. We have an activation function because when you multiply the input image by the filters, you get an output. This output will go into the next layer. But the values that we get out of this may have a very wide range. Let's say you get a value like minus 3,000, or you have a value up to 5 billion. I don't know, a very big value. So we don't want that because this is not very good for the learning of the models. So these activation functions, these are things that put this into a different set of constraints. Like, for example, between 0 and 1, like these, you know. So it makes the values between 0 and 1 again. And if the values are far from that, perhaps it's just threshold them out, just cut them out. So you can search for deep learning activation functions. Let's see, we got the first link. So I'm going blind with this linear function like this thing here, sigmoid function like this here, or let's see, the 10h function like this. So we have different functions to do that. Usually the relu is a very used function. So deep learning relu function. Let's oh, this is the relu. Yeah, this is blue one. So for a set of values from the input, we get 0 of output, and after that we get like a more linear output. So it's kind of a threshold of values for some inputs, and only outputs other values. So this is important to keep the network like on a very constrained number of values. And this input shape, if you remember here, we said that we had 28 by 28 pixels of input. If you had like a satellite imagery in this example with different bands, you would put here the number of bands. Like, let's say you have the RGB and the near infrared. Then you put here like 4. Okay, so this is the convolutional layer, and this code does all the job for us, everything. We don't need to know more about the mathematics behind it. The second layer, it's also a convolutional layer, so you can stack them to extract even more features from the data. And usually when you put more layers stacked, you increase a bit the number of filters. So now we have 64. We also have a 3 by 3 kernel size, use the same function. And now it didn't establish the input shape, but I guess it automatically identifies the shape. Okay, you already know more or less what the convolutional layer does. And now the max pooling. And the max pooling, it's a size of 2 by 2. So what it does is, for example, if you have a 28 image and you have a max pooling of 2 by 2, the output of this, after you convolute this small window through the image, in this case we have a maximum operator, so we get the maximum value we will have an output with half the size of the input imagery, like for example 14. So this operation, the pooling, and in this case the max pooling, we get the maximum value, for example, of this window here, but now it's here, the maximum value. It's more or less like this. The important thing is to get the maximum values and to reduce the dimensions of the information. And okay, let's look at the summary here, what we have. So remember, we set up the input 28 by 28, and the output of the first layer is 26 by 26 and 32, because we specified 32 filters. So now the dimension is 32. But we have 26 by 26. So why did it change? Well, if you have an image of 28 by 28 pixels and you want to make a convolution with a 3 by 3 image, you must think about how it's gonna work on the edges. Like how does this fit? So without specifying additional parameters, it will reduce one column here, actually, to reduce one column here and one column here, because it cannot fit the window perfectly. That's why we have 26 here. To fix that, for example, we can come here and edit this model and say padding equal same. Just let me run this and see if this works. Okay, now we have 28 here, because this padding parameter, which is another very important parameter for these models, it mirrors the image. So you have the exact same output size as you have the input. So when you put padding same, it mirrors the image whenever you need to make a convolution outside of the window. So it creates data, like it repeats this data here, repeats this data here, and does the job for you. So you use this when you want to reproduce, you have the same output as input. So if you use this here, and I also add it here, for example, now we have 28, 26, we should have 28, 28. So 28, 28. Now we have the same input. Will this improve my model? Not for this case, but this is this is important, for example, to understand what's UNet doing. In a UNet, usually use the penny same to make these mirrors, and when you predict over an image, it also improves the output, because so whenever you have a border, the values for the border will be better predicted. Okay, so we already go through the max pooling thing. The dropout is a more difficult concept to understand here, but I'll just explain it briefly. It's really written here: randomly turn neurons on and off to improve convergence. So this is a bit more advanced, but you can think that this is a technique to improve the training, so the model learns better how to predict the output without memorizing the training data so much. So what does it do is it will basically throw out, let's say, 25% of the weights it learned. So it will not memorize the data. So it's basically to learn better. Okay. And then on the next layer, the flatten, you see here on the summary, we now have a 14 by 14 image after the max pooling operation. And now we have an output of 20,000 values. So what is this 20,000? So 14 times 14 times 64, hopefully I got it right. Yeah, 12,544 values. So it's all of the values that we have on each of the features that we have now. So you can imagine that our original 28 by 28 image, it was then represented by a 28 by 28 feature with a dimension of 32 layers. Then it turned out to 64 layers, but now it's only 14 by 14. And then we make this a single vector of size 12,544. So it's a very big vector. And we connect this. So this represents all the image and the representations that the convolutions were able to learn. It's this single vector. And what we do now, we connect to that simple neural network that we saw in the beginning, like a multi-layer perceptron, like for example. But here we specify 128 neurons. So imagine 128 neurons. I will put this here. This is 128, and we connect each of these things here. So you can expect that between all these connections, we now have lots of new weights. So it's basically the 12,000 times the number of neurons plus some additional bias parameters. So now we have, let's see, 1 million parameters. So imagine it's a very big model to do this representation, okay? And in the end, we use another dense layer, but now we only specify 10 outputs. Why 10 outputs? Because we only have 10 numbers, okay? And now what we want to see is that for each of all that neuron thing, the 128, we only have 10 on the output. We only have 10 here. It's all connected as well, but we want to see this is number 0, this is 1, this is 2, 3, up to 10, no, up to 9 actually. And to achieve this thing here, we use a softmax activation function now. Let's see what the softmax activation function look like. Hopefully there's one here. Yeah, this thing here should be it. So it's a function that's more or less like a probability from 0 to 1 following this sigmoid thing here. And now the output will be a value from 0 to 1, a probability. So if the probability for number 0 is like 0, then it's probably not 0. Like 0, 0, but maybe for 9 it's 0.9. Maybe for 1 it's 0.1. For some reason it thought the 1 and 9 looks the same, and you have this probability. And now you have like what's the highest probability? It's this neuron, so it's 9. So it may be a bit abstract, but this is the basic concept of this model. We can now run this model with the next two blocks here. This block compiles the model, uses attributes loss function and an accuracy metric to so you can see the performance of the network while it's training. And the next one that starts with import math, it's the training. So this block now, it's what you see whenever you're going to train a deep learning model with this simple data set or with a remote sensing uh, imagery. It will appear something, hopefully, a second here. So if you guys are able to also follow up to this part, please say something in the chat. Yes, I'm following. So what's happening here? Um, we we told the model to learn the trained images, which were those 28 by 28 images, based on labels, which were just a number, like this is 0, this is 1, 3, I don't know. Train that during 5 epochs, which is like 5, look through all the data set 5 times. And this last parameter, it's a thing that the deep learning models, any neural network actually have, which is a type of way to adapt the weights. So what's the result of this? The result of this is 1875. So each time the each step, the model will look to 32 different images. So we have 60,000 for training. The model will look for 32 each time. So it looks for the 32 images and adapt the weights. 32 images, adapt the weights. 32 images, adapt the weights. And in the end, we have 1,875 steps in each epoch, where the model went through all the training data once. Then it does again. Then it does again. This number of epochs may vary with the problem you're using, you're studying. For some problems, for example, I use 300 epochs. For some problems, the model could be trained with 50 epochs. Depends on the problem, depends on the number of samples you have. In the right here, you see the accuracy on the training data, and you see the loss function, which is the sparse categorical cross entropy. You can Google that. But what we want to see here is the loss reduces each step, which is okay, it happened. And the accuracy, ideally, it increases each step at each step. So in the end, we were able to get 98.68% of accuracy on our model. So it's a very, very accurate model. This is based on the training data. So we can evaluate our accuracy. We can use this next block of code here. What it does, it applies the model to the test data. And we see that for the test data, it obtained an accuracy of 99.12. So it was indeed a bit higher than on the training data set. Sometimes this can happen, but sometimes it should also be lower. But ideally, it would be close, not very far away from the training data set. Because if you have if you have like a training accuracy that goes up a lot, and if you have let's see here, if you have this is train, If you have a test data set that does not reach the same level, you're probably doing something wrong. You can try and improve this model to close this gap here. Model is probably overtrained. Um, okay, so based on our test models, the model is very good. But let's look at the images that it outputs. So with this code, what does it do? It gets the test images. In the Google Colab, at least with Python, you can just hover your pointer over the things over the objects that you have, and it will show you some information. I don't think this works for R, but with Python, it shows that we have 10,000 images of 28 by 28 dimension and one layer, and we apply the model. We predict this with this input and save the results inside the spreads object. Then we get the maximum value out of those probabilities. So remember that we have 10, 10 a vector of 10, and we'll have like 0, 0.1, 0.9, 0, and go on until 10 values. So each of these is one of your values from 1 to 9. So let's see for this example right here, if this is number 1, this is number 2, this is number 3, 4. When we apply this operation, the argmax, it gets the highest value of the vector. So it gets this. So the output would be 3. And it does this to all of the 10,000 images. And so when we run this, it will apply the model and get us 5 random numbers. So I included this on the MIT code, so you can get 5 random numbers. So this is the input 17930, and the numbers below the inputs are the predictions. Actually, you can see here on this plot X label thing, we plot here the prediction. So we plot the test image and the prediction. So this is what the model predicted. For example, we have lots of different kinds of ones here. You can see it's very different from each other. And on your screen, you probably have different ones as well. Some of these 4s could be easily confused with a 9. But the machine is able to do that very, very accurately. And one last thing on this data, we have this thing from the original MIT code, which they created this MNIST Dream dataset, which is it's a video, these changing numbers that you're seeing on the screen, and we can apply the model for each frame of this video, so to predict the number in real time. So this code below here does that. So when you click on the play here, I'll not try and explain this because I don't understand everything that's going on here, but it will show a frame of the video and the output of the network. You see that mostly the model is very, very accurate. It's almost always 100% accuracy when predicting the numbers. Let's see if we can find one that's not 100. Oh, 97. It's reached a 97 on a 5, I think. Yeah. So it did that for each of the numbers, and down here you see the output GIF from the MIT original code that it's displaying on real time the GIF. This code should output a video as well, similar as this, but Maybe it's not updated. I didn't try to make it work, but if you have curiosity, you can try and make this work and generate this output, this animated output. But I find this very interesting. And so just to finish this part, to say that these models are not fixed. You can change them. For example, I can just remove like the second convolutional layer, for example. Just use one. And let's see what's the curiosity we get, just out of curiosity. What will you do? It will reduce the number of parameters as well, you know. It's less parameters to learn, so it will be faster. So usually we want models that are faster. Let's see if we get a similar result with a more simpler network. If you have any questions, please write on the chat, and the organization can read. So it's finishing here. Okay. So if you remember before, I think we got exactly this number here, 98.68. So we got a slightly lower number, about 1% less. Let's see on the test data set. Now we got 98.5. So it was 99 before, so we got a little less accuracy. But you know, 98%, we will likely not find an error here. It will probably all be 100% correct here. You can even, if you want to play with this, write create an image on Paint, like on Paint here. You can like draw a number. If you create an image of 28 by 28, you can even input that into your model and see if it works. Yeah, you know, this more simple model also worked. Let's try and just remove it. Another layer here. Perhaps we can even remove the max pooling. Just a convolution flatten and a dense. Let's see what happens here. Yeah, it's training very well, like 88 already. And let's see, number of trainable parameters, 3 million. Yeah, I think it maybe increased because we had max pooling, which reduced the dimension. Now we don't have it, so we have more parameters. That's why it's a bit slower. So you know, you can play with these models, try to achieve a better result. But this is more or less what we do once we have the training data set, which for remote sensing data is the first challenge. And I'll talk about this on the now on the sequence. So do we have any questions before we proceed?
Ricardo, just to let you know, there are no questions actually so far, but I just want to make a remark that we have participants online from Argentina, Brazil, Cameroon, Iraq, India, Israel, Kenya, Mexico, Nigeria, Mozambique, Portugal, Senegal, and US.
Very nice. Okay, so let's move on, please. If you have a question, just write on the chat. There's no bad question. If you're learning something, that's my goal here. So I put here a slide to call the attention for performance metrics. And this is more towards the remote sensing community, not the like the example we were looking now, because there are some metrics that may induce us to error. Like for example, this image here, we have like water, some boats. Let's say we want to segment these boats, and let's say this is the training data, and let's say this is the prediction. So if you take into account the accuracy of this model, the performance metric accuracy, it will probably have like 95% accuracy, even though it didn't map like anything, because you're accounting for both the absence of bolts and the presence of both. We don't have any presence, but the presence is very little in our image, and the absence is huge. But the absence is 95% correct. So call the attention that some metrics are bad when you have like imbalanced data sets. So to prepare for that, for example, there are metrics like the precision, recall, and F1 score, which looks more into the target than the background. Let's say, like the presence of the target rather than the background. So these metrics, like these three, these are very good for class imbalance. Also, when you have multi-class segmentation, um, let's say you want to classify uh, bolts, containers, other class, I don't know. You may have like three classes, uh, and you have like accuracy for each one of them. So for one of them, it can be good, like very very good, 100. For other, maybe 80. But for other one, maybe very bad. So you can also calculate the average precision between classes to obtain a more reliable estimate of what you are achieving. And the last one, which is one, it's a bit new for people from remote sensing, like more traditional remote sensing, which is the IOU, which is called intersection over unit. Um, Basically, if you have mapped, let's say you have this polygon, which is the reference, and you map it this area. Uh, this is the prediction. So reference prediction. You see that there is an area of agreement between it. You can calculate, for example, these metrics using this agreement and say the recall, the precision, etc. But you can also calculate the IOU. And what you do is first get the overlap, which is this part. So let's say this is um, 60% of all the pixels. And all the pixels, so we have, let me put another color here. All these pixels here is the area of union. And all the pixels accounted for 120, let's say. So when you calculate this 60 by 120, what you get? 0.5. So you could say that although the prediction it matched the reference, perhaps that's enough for your problem. But the polygons, the spatial congruence between the polygons are not very good. They could be better, like they are only 0.5 IOU. Um, and then you may use a different model, a different architecture. You may improve your training samples. Sometimes this is just a problem of a training sample. I had an application for a paper that's under review right now, which is I want to map the palms. So let's say this is a palm tree. How did I draw the training data for that? I draw more or less like okay, this is it. So if I compare my training polygon with the actual palm crown, it will give it will give there's a very good overlap, but my polygon has much more area than only the overlap. So my IOU would would not be one, would be less than one. You know, so if I wanted to cover exactly the palm, I should draw a sample more like closer to the palm. You know, and this is also a thing that different architectures can solve as well. Make more smooth segments and this kind of things. So pay attention to the metrics.
Ricardo,
Yeah, yeah,
just to interrupt you, there is I think, a pertinent questions from Sibeli Amaral. I am
yep.
projecting here on the screen, and she thanks actually for the talk, and she has questions on training images. So you use both training samples from objects of the training scenes, train both, and then apply the model to a broader, larger image. Is that right?
Yeah, this is the example, right? Is that it, Viraldo?
Yeah, exactly.
So what again was the question?
I put it on the screen.
Yeah, but I'm not looking to the screen.
Okay, okay.
Sorry.
Uh, sorry. So, she write like this. So you use both training samples from objects of the training scenes. Train both and then apply the model to a broader, larger image.
So that's the question.
Yes.
Yeah, yeah. Basically, that's it. For example, if this is your data set, actually this will be a bit hard because there's not many bolts on this screen. You should have more bolts to train a model. But imagine you have a dozen or 100 of these small images with the masks. You train a model. You see that same training procedure of the MNIST, the same thing, the same kind of thing, and um, and then you apply to a different image similar to the one that entered the training. So now for now, look at this image, you try to segment the bolts here. Yeah, that's it.
Perfect.
All right. So now going to a more broad pipeline of doing image segmentation with remote sensing images. Uh, I tried to come up with this workflow, which is more or less what we do to make a image segmentation. So we have some image. Let's say it's a Sentinel-2 image with a few bands, like let's say RGB, near infrared. Okay. Then you have a class definition. What do I want to map? I will show you example in a while that we want to map a crop, for example, rice crops. So I want to map rice. So what do I do with this? What the first step? I want to delineate samples. So what do I do on the traditional way? I have my image here. I have let's say some fields of rice. I place some samples, I get some pixels here, like some coordinates. Ideally, some coordinates that you went to the field and look. Oh, this is indeed rice. Okay, this is the this is rice. No confusion here. So I have this thing here. Okay, then I extract the data from the image for each of the pixels. I do some type of cross validation, but let's say it's a very simple one. With I split the data between train and test. I train a model. We can say like a random forest model that will try to use the inputs like the RGB, near infrared for each of those samples, and we'll try to estimate if it's like rice zero, not rice or rice 0 1, let's say. Then we validate the model using the model that we built with a test data set. And after that, we get the image from the beginning. Actually, I should probably put a arrow here with the model here, and we make the prediction. So now we have rice for all the image. This is the traditional image segmentation pipeline, okay? So what's different with deep learning? If you see, this is after, before, after, before, after, before. The orange boxes are basically what's different. And I will explain a bit what's different on each one of those. So the first thing we have here is patch definition. Then we have a different way of delineating samples, a different way of extracting the samples. We have this extra step of data augmentation, and the deep learning per se, the training of the model and the prediction of the model are only these two boxes. Okay, so this is where the deep learning model goes. These other parts are before the deep actually the data augmentation is within the model, but I mean these other parts are before the model. It's about data preparation. So the first thing about patch size definition. As I told you, we do not use pixels anymore with the deep learning. We use patches. And defining the patch size is an important thing because it should cover usually a bigger area than your object, than your target. For example, my target is this little palm trees here. I want to have a patch that has both the target but also other stuff. The absence of palms. The model won't know that there's a forest. The model doesn't care what we are mapping, but we know these are forests, these are gaps in the forest, these are other trees, anything else. So we need to have background for the model as well. So other thing that affect the size of the training patches is the hardware, because we cannot, for example, we could try, for example, and use this whole image to train a model. No problem doing that. We could use it if we had a very good hardware. Let's say this is a 10 kilometer image. Imagine the convolution of that. It will be like horrendous, like too slow. But if we get smaller patches, you can start to think like how the model can do that more efficiently. If we had lots of small tasks, we can do that in parallel. I will show in a while what's that. But usually we want to have a patch of around 128 pixels, perhaps could be 24, could even be 32, but could be a bit higher, 256. Now depends on on your hardware, on your graphics card, okay? Because this with the increasing size of the training patches, more memory it will use in the hardware. There is no optimal definition. You have to choose one, see if it works, change it a bit, and see what works best for your application. This third thing I already told you about, the contextual information. In this example, the patch size was 128 by 128 pixels. The pixel size was 0.5 meters, so it's a very high resolution data. This is not an optical imagery like you see in the Google Maps. This is a LiDAR canopy height model. So the values here are the height of the canopy, the first canopy. And each of these patches, if we multiply this by this, we have it's 64 meters. Okay. So the second thing is about samples delineation. And I showed this example from this paper that please concentrate on these first two columns here. We have the input image. It's more like a coarse, not very high resolution image, so you cannot see exactly what's going on here. Perhaps it's a building, you know. But imagine that the target here would be like this area, like it want to map this area. So we make these dense labels. So we make the polygons that encompass the target class that we want to map. So this is called dense labels in the deep learning terminology. So this is what you will do on your applications. You create labels for the thing you want to map. Then you convert these polygon labels with to a raster. So from polygon to raster. Okay. There is also still in development new ways to do this, which is called weak learning. Which so instead of drawing all these dense labels, which may be hard for some applications, you can probably just get one pixel here or one pixel here, one pixel here, one pixel here, and the model may understand what's going on. Okay, so this is but this is a bit still in development. I still didn't use this. Later on, if Raul perhaps want to complement that, perhaps someone from his team already applied this. But usually you want to do this, to draw these dense labels. So polygons covering all the area that you want to map. So not pixels, you want to have the polygons that we convert to rasters. And so what we have after this sample delineation is this kind of thing. From the traditional perspective, this is what we have. Each row is a pixel. Each column is a band, and we have a class like rice or other things, background, let's say. And in the deep learning, we have the dense labels, like I said, the image here on the right, the label on the left, label image. So these are real examples that I'm going to show you an example real time. If the Google Colab code was working, you would be able to run this example in the Google Colab. So I'm sorry it's not working today. But you can imagine that to get from the whole image to these patches, we have to do some procedures to crop them out. Okay. In the GitHub, there is a code that does everything for you. So if you want to apply this kind of thing, you have the code already in the GitHub. So you can see here like rice field. So this is the rice field, rice field, rice field. Okay, we can easily see that on these images, these patches. So this is what the model is going to see. An image with some bands and the label to learn how to map. And the last thing that's different, data augmentation. So this is a process that does not exist in traditional machine learning, as far as I know, but it's very important for deep learning, especially with remote sensing image. Um, actually not especially for remote sensing image. It's important for all applications. So see this cat here. The cat is located here on this position. On this different picture, imagine it's a different cat. But now the cat's slightly to the top. Now the cat's slightly to the right. Now the cat's slightly to the bottom here. These are all cats. It's all the same cat actually, but the image is a bit different. It's skewed. It's changed a bit, but they're all cats. We want to teach the model that scale is not very important. It want to detect the features, like to understand the eyes of the cat, to understand the ears of the cat, to understand the fur of the cat in any perspective, in any way possible. We want to flip the cat. We want to stretch the cat. We want to change the color of the cat to blue. I don't know. We want to change everything on this image and teach the model that this does not matter. These are all cats. Okay, you got it. So we do the same thing with the remote sensing image. Like for example, we get let's take a easy example here. For example, we have this thing here, and we get this image, and for example, we rotate it. So now these features are like here, for example. It's still the same thing. It's still rice, but it's rotated. That doesn't matter. It's still rice. We may have a zoom, like I don't usually apply zoom to my remote sensing image deep learning, but you could. Like, it's a very big field now, very big, like the same field, you know. So you use this uh, data augmentation techniques to show more variability of the signal to the model, and so it understand that scale can change, but the targets are still the same. All right. um, Let me just see how many. Oh, we are about to end the slides here. After that, I give a 5-minute break before we go to R again. So what types of remote sensing data we can use? Any type. You can even combine different types of remote sensing. The fancy name for that is fusion, data fusion. You can write that on a paper, on a proposal to your boss, and wow, data fusion. Okay, so this is becoming very common to do, like combining optical data with SAR data, even LiDAR data, all together in the same package, and the model understand the differences of the image in regards to what you want to map. You can put everything together or individually, and all these different data all work. Okay, even the LiDAR data. And in the LiDAR data, I showed you an example that I used the canopy height model, which is basically the height of vegetation. We see the tree crowns, we saw the palms, and here you have the height. But we can also use the the point cloud of LiDAR data. So imagine these are not an image anymore. This is a 3D environment. Let's make another axis here. Like perhaps this should be Y and this should be Z. Yeah, this could be 3D. There are networks that does that. If anyone is interested, look for point net. So I think Sibeli, if Sibeli is the same Sibeli I know, she's probably wondering about using the LiDAR data with this. So yes, you can use it. I still didn't use that, but I plan to use for the Palm thing. I only use the CHM, which is a 2D representation, only 2 dimensions, X and Y, but you can use the 3D information as well. And now the thing about the GPU that perhaps you were, what's GPU? What's all that about? The CPU is your processor in your computer. Like you have a Intel i7, let's say, or AMD something. This is the CPU. And the CPU, some of the modern ones, it has like 4 cores or have 8 cores, you know, and you can split different jobs within these cores. So this our processor can run like 8 different tasks at once. So imagine that that image patches that we want to train, it can split the computation that we do on the model with these cores, okay? But and this CPU, it's fast. It's very fast. It's very fast. But now we have the GPU, which is this truck here. The truck may be slower. Uh, Maybe because some truck drivers there, they drive very fast. Okay, so but they may be slower, but it can carry a very bigger load, a much heavier load. So instead of having like 8 cores, it may have hundreds, thousands of cores inside of the GPU. So these cores are slower. Let me put here like hundreds of cores. They may be slower than the CPU, but they working together, they go farther, you know. And there is a test on this link. I will send you the presentation afterwards on the GitHub repository, probably tomorrow. And you can, if you're interested, you can run this example here, which shows that GPU was 85 times faster than CPU at doing one convolution layer. So this is just an example of how faster a GPU can be. And I suppose it can be even faster than that. But this is just an example. So this brings the importance of having GPUs to do to do deep learning. They are more or less a constraint to use deep learning nowadays, because using only the CPU is very slow. Okay. So which language and platform can I run deep learning? Within Python, you have these libraries. Within R, you have reticulate, which basically makes Python inside R. And then we can run the Keras and TensorFlow libraries, which are the core of the deep learning methods. So remember the code we saw. Let me show you on this thing here. If we go to the start here, you see this is the Python code, okay? So it imports the TensorFlow library and the Keras, okay? So these are the backbone, what makes the deep learning runs. Um, so these are two languages that you can apply it. You can also run in other languages, C++, etc. But thinking about a more easy way to apply it for science and for data science applications, it's Python or R. And you can run in your computer if you have a GPU. Most of the modern laptops, they already have some kind of GPU attached. So they're usually not very fast, but they can run some algorithms. Not very heavy models, but you can run. So ideally, you have a machine with a GPU. For example, I have a RTX 2060 Super GPU. You can Google it. It's a very good GPU. There are others much better than mine as well, but mine is one. It's a very good one. Or you can run for free in the Google Colab. That's what we did with the MNIST. We ran in a GPU environment for free, that MNIST dataset. I put here that's ideal for beginners because it's it will not allow you to run very big models because it has some time constraints, and also it's limited on memory, on hard drive, and all of that. But it's good to begin. Uh, Now again, apologizing because the we had this R code, which is the this session 3 in the GitHub. It was a code within Google Colab that we would run the crop example. We would train the model. Uh, I can even open here just to show you that there is a previous run here that worked. Like, uh, let's see the result here. Like, it trained the model, it predicted the classes, so it was working a month ago, but for some reason right now it's not working. So I'm sorry that I'm not able to for you to have this experience with this real remote sensing data. But you can, if you have a GPU, you can run in your computer. Okay, the data set is all on the repository on GitHub. And the last thing, which which is a very attractive choice for more operational applications, is to use a paid virtual machine. So you pay for Google, for Amazon to use their virtual machines that have the environments that have a GPU so dedicated for you to run this. Um, and you can use that if your project has money to pay for it. But I would say that to run a lab like on a university, you should probably just buy a GPU to make things running and get to run the models. And if you want to scale for a more robust application, then you use virtual machines. And another thing, when Raul asked me to bring you this lecture, um, he wanted to run everything in the cloud. Let me see. Oh, the slide is a bit too far. Sorry, I'll get to that in a while. So just getting back to this slide, I put that the collab or the part where you need the GPU is here. It's a model training and model prediction. All right. So these are the two steps you will will likely not be able to do with only a CPU. You need a GPU. All right. And how to use it on your own computer. I have this link. Hopefully, the organization can paste it on the chat. It's the link for the installation steps. I can even open this on the Zenodo platform. If you cannot find the link, you can. Oh, it's kind of slow. Okay. I'll keep talking here. Maybe it opens. So this is like a guide on how to install TensorFlow and Keras on your computer. How to install the drivers of your GPU in order to run deep learning in RStudio. Um, but this is for again. This is for NVIDIA GPUs and Windows. If you use Ubuntu, for example, Linux distribution, um, there are ways to install the NVIDIA GPU, but we had some bad experiences in the past, so we opted to run on Windows. But if you're very good with Ubuntu, try to install the NVIDIA. Good luck. And I'm not sure if there are applications with other graphics card. And so you can download this PDF here, just push download here, hopefully downloads. It's a kind of slow. And on this PDF, there are all the steps to install. There are some steps here also on how to install the Conda environment. If you have difficulties on installing this Conda environment, please go to the GitHub repository and take a look on the RGE pre-installation video. because on this video here on step 1, I also install a Conda environment. So if you have trouble with the Conda environment, go to this video as well and take a look there. But this is the basic steps for you to run on your RStudio inside Windows and R, okay? I'm not sure how to install it here because it's already installed on my machine, but it's not very hard. If you have any questions, you can also email me, okay? And the last thing about I was talking about is how asked me to how we can make deep learning entirely in the cloud. Um, and I wanted to try this challenge, and I built a code that went used Colab as a platform because it can talk to GE through RGE, and it could run the deep learning uh, from inside, and then we would have the blue. We would have like a map as an output, so running entirely on the cloud. I made this script, but I was not able to make it very, very like efficient. So the first part that I will show you after the break on preparing the data, cropping all of that, we'll see with the code. It was not very efficient to run in Google Colab. It was kind of troubling. So I was not able to do this first part in the cloud. So I did that. I did this first part on my computer, so locally. And this is the past week lecture. If you're interested in RGE, if you didn't come last week, you can go um, to the event YouTube. You can find the video for the last week lecture, which we use the RGE to extract the data that we are going to use today for the demonstration. Okay, so I did this locally, and then the output from this local thing would be the patches from images and the patches for the labels, and then we'll put this inside Colab to train. So use the GPU from Colab. So we did that on a previous workshop that I gave the code on section 3 that I talked to you about. But when I went to run it again this week, it didn't run. They changed something in Colab code. Perhaps it would run if the code was in Python, because Colab's more natively with Python, but it didn't run with R, sadly. So this is something to check in a few days, a few weeks. It still runs with R, or if there is a change in code that we need to establish in the beginning. But right now I cannot make this work with Colab in R. So what I will show you is how to do that in the local machine as well, because that's what we can do. So we apply the deep learning local machine and to get a map out of this. So the cloud process in the end, it's basically just to get the data. So we get the data from the cloud, from RGE. We push it, we download it to our machine. We can apply a deep learning model here, produce a map, and then if we want, we can like delete the original data, download more, apply the model. We can make this like a for loop from inside the programming language. Okay. So I think that this will be very hard to apply on Google Colab because of the limitations with time, after my experience. But this should be doable with paid virtual machines from Amazon, from Google, which should be more robust, should have better parameters like time to run the stuff. So I expect this to work. Okay. but this takes money, and then sometimes we are not very happy with this. But right now, the cloud, in my perspective, it's mostly to use the RGE, or you can use the EE with Python, and apply the deep learning in the local machine. So right now, this is the thing. Just before I end this part here, we have some references. I like this book very much, Deep Learning with R from Cholet and Allaire. It has examples, it has explanations for the models. It's a very good book for anyone starting with deep learning with R. I think there's a version for Python as well. There's also this thing here, the website for TensorFlow Keras, which also has some examples, documentation for the functions, everything, and a paper that I found a while ago, which gives some perspective on the applications for object detection and image segmentation with deep learning that you may take a look. So focused on remote sensing, all right? This is a good read. So this is the more lecture, and we had some exercises before. I think we should take a 5-minute break now to go to the bathroom, and then we go back and I show you with the code in R, okay?
Perfect. Ricardo, just let me know. I will just start with the announcements of the forthcoming activities, and then we will return in 5 minutes then. Thank you.
Okay, I'll be back in 5.
So I will just make some announcements, but if you want to take actually some short interval, please feel free.
Que satisfação falar com vocês, dar as boas-vindas ao evento, dizer que a UNO Chapecó, nos últimos anos, com seu foco na pesquisa, no desenvolvimento da inovação como instrumento de desenvolvimento da região, acredita muito em atividades como esta, um evento importantíssimo que trata de sensoriamento remoto, que trata do uso de plataformas não tripuláveis para atuar principalmente na área agrícola, né? Uma área que nos interessa muito. Nós somos uma região que produz muitos produtos, uma região da agroindústria fortemente constituída por nossas cooperativas, nossas associações, e por isso fica aqui o nosso sentimento de felicidade de participar desse evento. Desejo que seja um sucesso, que possamos trocar muitas experiências, conhecimento e desenvolver essa área. Sucesso, parabéns a todos, sejam todos muito bem-vindos, em nome da UNO Chapecó.
Well, this was a message from the rector of UNO Chapecó, that is one of the partners of the organizations. And now another short welcome talk from our rector from the Santa Catarina University.
Olá a todos vocês. É uma honra dar as boas-vindas aos participantes deste evento, que é estratégico para Santa Catarina, para o Brasil e para o mundo. Destaco que localmente estamos organizando este evento junto com a UNO Chapecó, que é motivo de orgulho para nós da Universidade dos Catarinenses. O evento conta ainda com o apoio também da Fundação de Amparo à Pesquisa de Santa Catarina, a FAPESC. O evento nos orgulha, já que a UDESC vem melhorando a sua classificação em rankings importantes internacionais, graças aos investimentos que temos feito, principalmente nas áreas da pesquisa e inovação. E a temática do evento de utilizar drones na agricultura e na silvicultura vai de encontro a isso. Dito isso, em nome da Universidade do Estado de Santa Catarina, que tem como missão formar quem transforma Santa Catarina, desejo um excelente evento a todos. Muito obrigado pela atenção.
So, in between, just another video, and then we will start the lecture again.
Hi everyone, my name is Cheryl Rose Reyes and I currently serve as the president of the ISPRS Student Consortium. I am very happy to welcome you all to the 7th edition of the IEEE GRSS Young Professionals and ISPRS Student Consortium Summer School this year. On behalf of ISPRS and the consortium, I would like to thank all the organizers who continue to persevere in developing this virtual event in light of our current global situation. This is the second virtual edition of this summer school. I would like to introduce you all to the ISPRS Student Consortium. We are the official representation of the youth to ISPRS. Our main goal is to link students, young researchers, and professionals worldwide interested in photogrammetry, remote sensing, and spatial information science, and to promote their scientific and professional developments. We advocate imaging and geospatial science for informed, scientifically valid, and technologically sound observations of Earth conditions and trends that lead to improved and effective decision-making. I work together with members of the board of directors from all across the globe. Charles from Uganda is our vice president. Charmaine, who is currently in Ireland, is in charge of our newsletter. Mustafa, our social media coordinator, is from Turkey. And finally, Sonia from Azerbaijan is our website administrator. The consortium also publishes an official newsletter called Spectrum, and it is named as such because this publication is envisioned to cover the broad applications of remote sensing, photogrammetry, and spatial information science, and to welcome contributors from diverse backgrounds and fields of discipline. We publish 4 issues a year and from time to time publish special issues. Our most recent publication is on the applications of unoccupied aerial systems for environmental monitoring. One of the major events that we host and coordinate every year are the summer schools. Since 2017, we have been hosting a minimum of 3 summer schools per year in different locations around the world. These summer schools provide opportunities for students and professionals alike to further their knowledge in remote sensing, photogrammetry, and spatial information science at a minimum cost, and to establish their professional networks by providing an avenue to meet and connect with fellow students, young professionals, as well as professors and industry experts. We are again very grateful for the local organizers in Brazil who are hosting the second virtual edition of this summer school, and we look forward to the webinars, the roundtable discussions, and the hands-on sessions. The consortium currently hosts the virtual rooms and the webinar series to provide our community with more opportunities to learn and interact with experts in our scientific community. The webinar series was conceptualized in 2018, and we have organized webinars on Google Earth Engine, computer vision, and machine learning. The virtual rooms was developed by the board of directors as a way to keep the members of the consortium connected during this challenging time and to help them navigate this new lifestyle. All the resources for the webinar series and the virtual rooms are available on our website and our YouTube channel. The Leadership and Service Mentoring Program was launched in December 2020. This program primarily aims to train and familiarize qualified individuals with the responsibilities of the position they are interested in and about the activities of the consortium. We are currently training 6 mentees from different countries who are interested to lead the consortium in the future. You will find most of the recordings of our virtual events over our YouTube channel, and one of our most viewed videos was from the Brazil Summer School last year. The consortium also works in collaboration with the Ladies of Lancet, the Sisters of SAR, the American Society for Photogrammetry and Remote Sensing Student Advisory Council, the Mato Grosso do Sul IEEE GRSS Student Branch Chapter, the ISPRS White Elephant Club, and the Asian Association on Remote Sensing in organizing a monthly virtual event called GeoMixer. Inspired by the GeoMixers organized in previous conferences, this event provided a platform for remote sensing scientists at all career stages from around the world to build their professional networks. Finally, we invite you all again to register as an individual member of the consortium and to join us on social media. We are on Facebook and Twitter, and if you need any resources, please do check out our YouTube channel. Thank you very much and have a meaningful virtual summer school.
Wonderful. Those were the words of Cheryl Rose Reyes, currently the chair of the Student Consortium of the IS Perez. Well, I will add again our speaker and also the presentations. So welcome again, Ricardo. Please feel free.
Thank you. Let's go. So on this second part now, we will look on a real world application, which is mapping rice crops. The data for this application we learned last week how to download from RGE, from Google Earth Engine using R. You can find on the GitHub the data set already available in this Zenodo link, or even on this RAR directly here. But you can enter the Zenodo and take a look in there. And now we will use this first, this code number 2, applying deep learning to satellite imagery, which basically start with the raw satellite image, prepares the image crop into patches, train a model, and predict for the image, show the accuracy, and plot the map. So this R code does all of this. I intended that to show you that you had the experience to train the model yourselves using the Colab based on the already cropped data. But as I told you, this will not be possible because Colab is having something right now. It's not working. Hopefully it will be fixed in the future. But if you have a GPU in your machine, you can now watch the demonstration now and then run everything of this script, okay? Okay, so let's go. This is the code deep learning crop, which is found in the code here, like deep learning crop. The this code, so the first thing to do here, it loads and install a few packages that we use in the application. For those who not know, this is RStudio. You should have that installed as well. And so this is the basic packages. This is the directory for the TensorFlow environment that you should install to run deep learning on your machine. So this is explained on this link. This link I showed before on the Zenodo. There's a guide there. And afterwards, also you should have the data set, and you will set up the directory. So the directory that we put here should be where you're going to place the data and do all the computations, all right? So there's also the OSGL thing here. I'm not entirely sure we need this installed for this application, but in case you have that installed, also set up your OSGeo here. So we just run this first part. This part you'll probably not be able to follow me unless you have downloaded the data set. Then you can do the pre-processing. And if you have installed the local GPU, then you can do the deep learning. Otherwise, just chill and take a look, try to understand, and then you can go back afterwards and with everything installed, then you can run. So this first part, I just run these two first sections here, up to the functions, to the end of the functions. So these are just functions we use in the middle of the script. Now we have this field data. We've come with the data set that I told you. So these are a shape file. We open it with read OGR, These are the shape files of rice crops for a whole state in Brazil. I got this from the Conab. Conab, I think this is one. Let's see. Perhaps the other link. Conab, this. Yeah. Mapeamentos agrícolas in Portuguese means like crop mappings. You can see the mappings. It's basically shape files for areas that rice has been planted in this state of the Brazil. So this is South America, Brazil, and this is a whole state in Brazil. And these are all the crops of rice crops fields that we have. And for this exercise in the previous lecture, we already downloaded the Sentinel data for one of the municipalities here of this state. So it's called Uruguaiana municipality. So we filter this field data for only the polygons over Uruguaiana. And when I plot it with the thing here, we see this bell-shaped thing here are all the it's the municipality perimeter and all the field crops. If you going to start an application, you don't have these delineated patches. What should you do? Well, you should get yourself a satellite imagery and map whatever you want to and create samples for whatever you want to map. Let's imagine this was a satellite image and I want to map this green area. Then I would like create samples around this, all right? This is a very bad example, but you'd delineate yourself some samples for wherever you want to map. Let's say I want to map water. I would select samples for water, all right? Of course, with much more detail, all right? Okay, so starting from that, we have these samples for rice. And let's see if this thing works. If it works, it should display. Oh, this is not working very well. Oh, okay, I can show you an example here. Let's say I want to map these crop areas in this location. I would, of course, create this within like a QGIS or ArcGIS. I would create my samples for whatever I want to map in a GIS software and have it done, all right? And then this is just a technical thing inside here just to find the list the images. So the image is inside this folder image. We'll have this file, Sentinel data, February 2020, single date. This is what we downloaded last week on the RGE course and is present on the data set on GitHub, okay? So if you didn't participate last week, you can download the data set. We will use it only the bands 1 to 4 because the model I'm showing right now has some limitations to number of bands. Actually, it's not the model. It's how we prepare the data. The PNG files, they only allow 4 bands. So this is something we are still to improve on my pipeline, on my team's pipeline, to use TIFF instead. So because TIFF would allow like much more bands, all right? So for now we are limited to 4 bands because of the way we pre-process the data. So this is just a technicality. We find the data here, and now is the first thing that I told you about the patches. We load here one image. I'm going to plot it on the screen. So right here. Takes a while because it's very big. I will show you what's inside this image object as well. Okay, so this is our area. It's a Sentinel image with 8 11,542 by 11,089 columns and rows. So it's a lot of pixels, like 94 million pixels in this image. We have originally 5 layers. As I said, we are going to use only 4. The fifth would be an NDVI that we calculated on the last week lecture. So this is our area. And for this example, we use a patch size of 128 pixels by 128 pixels, which I said is a common number of pixels that we use for deep learning. And since the Sentinel data has 10 meters of spatial resolution, we can imagine that each patch will have 1,280 meters, so 1.2 kilometers. What we want from this would be one sample for the model, all right? So you gotta start to imagine that you need lots of patches delineated, lots of, or to decrease this image size if you have not many patches delineated, all right? So we define this here, and what this code here will do, it will create a grid for us with this 828 by 828 size. So look at here, we have this grid here. So this is just done by this raster to polygons function. You can take a look more in detail later on. But basically, we create this 128. Each of these squares is 128 by 128. All right. So now what we want to do is crop the image for each of these small patches. So this is the next part of the code. I wrote here, the aim of this part is to crop the image into patches that we just created for the locations that we have samples. So we don't need to crop for everything, we just crop for locations that we have samples. And this takes 15 minutes. Okay, it will be a bit tight to do this. I'll just run an example, and then I will change the, let me see here. I will change here the line 677. I will run just the size of this. Let me take a look first. Wait. So in this image, we have 5,829 patches total. I will just crop, let's say, 500, just to show you the patches being created. I'll just run this. And what this code does, it's already have this for each function, which runs in parallel. So that's why we create this parallel cluster before with the number of cores that your computer is able to run. In my case, is 7. Hopefully I set 7. Yeah, number of cores here, I set as 7 in the beginning of the code. So I'm running this in parallel with 7 cores. So let me find the folder that I'm creating these images. It's still empty. Let's wait a bit. So what this code does, it will intersect the image with the grid just to check if there is image everywhere in the grid. Then it will crop the image based on each one of those patches in the grid, crop both the image and our samples. And if you go up here in the code, we use this function fasterize, which does something like this. We have the fields. These are vectors. What this fasterize thing do? It will convert it to a raster for us. So now, for example, we have it will be on very on high resolution. You know, this is just an example, but you have just values for wherever we have the samples, right? So now it's a raster. So that's what this line does. And so inside of the loop again, we crop both the image and the samples, the labels for our class. Let's look at the folder again. Oh, we have some crops already. So when we look to the crops that the computer is creating for us, it's actually already stopped. Okay, it already stopped. So for 500 things, it took 2 minutes. Okay, that's not bad. So it started 11:34, finished 11:35 here. So these are the labels, all right, that we just cropped for each of the sample, each of the patches. And here on this different folder image is it's the images that we cropped. So let's just so you see the similarities here. I put the labels on the left and the images on the right. So hopefully we see something very similar. For example, the 314, it has these rectangles. If we look the image, it also has these rectangles here. So this is one example. Let's see another example like this and here. Yeah, so you see they are matching. All right, it's important to check this because sometimes the computer, the for loop that doesn't work very well, and we end up with unmatching things. So now I will just rename this folder here to something else and rename my other input again, because this input I had here is already, everything is cropped. It's 2000 files. So if I have here 2145 of these patches, that means that I have 2145 samples for my model, which each sample is an image of 128 by 128 pixels. Okay, and we have both the image and again the label. Like, let's see, the image does something like this, and then the label, okay, the label it represents. All right, so these are our samples. If the Google Colab was working properly, you would be able to use these samples inside Google Colab and train a model in Google Colab yourself right now. We did that on a previous workshop last month, but I'm sorry we're not able to do that. So let's just continue here. Here's just another example. Load visualizing some patches. Let's see what's this. I don't recall if this is working. It's probably not working. Okay. Perhaps I didn't run this. Not found. Not found. Image there, class there. Where is this? I forgot to run something. Image there. Okay, it was here. I didn't run these lines on the step 2. Okay, sorry. Then we go back here. We will plot some samples. For example, this is one area with samples in green. And then this is the area. This is the bands, like band 1, 2. I don't recall. Band. Let me see. Image. Band 2, band 3, band 4, and band 8. I think this is the near infrared. And this is the samples. You can see they have some matching that we expected them to have. And we also have some data visualization on step 5 using a different approach with this magic package. It's the same thing, just showing that the samples match. Important to check this, that they're matching. Otherwise, the model will input some very strange stuff. And step 6, this is where I'm going to run the model in my computer. But if the Colab was working, you would be able to run on Colab. So here I am setting up only 15 epochs, so the model will see the training data set 15 times entirely, 15 times. I could set this up to a higher value, and but in this case, I just use this. The batch size, as I told you, how many images per step does the model see, learning rate, decay rate, etc., number of layers. I'll just put this to run, and then I'll explain the model inside. So this is a very big chunk of code. We can run it until almost the end. Here on this part, clear GPU. So if you were able to install the TensorFlow carriers, downloaded the data, you can run up to here, let it run. And now while it runs, let me increase this here. You will show, this is screwed up, it should be correct, but it's just visualization that's bad, trust me. The model, okay, the model. What we do here is we define the model, our UNet, if you remember correctly. The input shape of our UNet is 128 by 128 and the number of layers, in this case 4, all right? The number of classes that we want to map is just one, it's just rice. If we had a multi-class problem, we would increase this to a higher number, all right? Then we have for the UNet, let me find the UNet here again. UNet, here, the UNet. If you remember that I told you, this is like the first, these are the convolutional layers. So each of these big square thing is one of this line. So from the MNIST example, this is how we write it in R. So the number of filters, kernel size, and padding to mirror the images. Two additional things, a normalization, I'll not explain this here, but this line helps the training a bit. It helps the constrain the values, the activation function, and then goes into another convolutional layer. So if you look to the image here, there's one here, another here. So this is the first line, let's say, of the UNet. Then it should go to smaller dimensions. So where do we do that? Here, max pooling 2D with a pool size of 2 by 2. So if you remember, when we do a pooling with 2 by 2, we reduce the dimensions in half. So now, if we have 128, we should go to 64. So that's what's happening. And then we do, then we do 2 convolutions, pooling, 2 convolutions, pooling, 2 convolutions, pooling. We have a flat vector right now. Then we go up, and then this is the up convolution. Let me find the center. So each of the layers right here, you can see. So here is the center part. And now we start, well, actually, this is the center part. And now we start to go up sampling. So now instead of conv 2D, we use up sampling and concatenate. So this will now increase the resolution of the image back towards the original resolution. So this is the second part of the model here going up. So you can see it's basically the same thing as before, but we start to like reduce the number of filters going up, going up, going up. In the end, what we have a last layer, which is similar to a like that very simple neural network because it's a kernel one by one, and we have a sigmoid function. So if you remember, the other problem was a softmax, but now we have a sigmoid, more like this. It will put as well a probability of the pixel. So for each of pixels, we have in the image, it will put a probability of that pixel belonging to class rice. So if that probability is exceeds 0.5, we can say that this is rice. All right. If it's less than 0.5, then it's like other or background or anything. Okay, so this is what runs inside the model. It's very similar to the MNIST. It's a more complex, but it's very similar. The data augmentation that I told you about is this part here, from the B random B brightness saturation who up to this part here, to the create data set. So what this part do? It will randomly randomly change the values of the pixels, so the model understand that perhaps just changing a bit the values, it will not be a different class. All right. And we also do rotations. Let me remember here. We also rotate the images, so it gets the understanding that rotating those fields, they are still rice. All right. So this is already inbuilt in the model. The model already did this for us. We don't touch it anymore. If you were looking to the things that appeared on my screen while I was talking, you see that the model ran. So each of the epochs was here. This is the time it took for each epoch. And here, a difference from the MNIST. So for MNIST, we had this part. For this test, we also had the test data set already here. So if you look to the graph here on the right that it was creating on the fly, you can see the green is the validation and the blue is the training. So it started from the first iteration with a very high accuracy. So this graph on the bottom is the accuracy, more or less accuracy. It's an accuracy metric, right? We start with very high accuracy with training, but a bad accuracy with training, with test, with the test data set, with the validation data set. And we see that at some point the model started to make good predictions, and this is we can say that the model is able to generalize the information. Okay, so now it learned the patterns and is able to generalize to a different data set. So in the end, what was the accuracy? If you remember from the MNIST, training accuracy was 0.75, validation accuracy 0.75 as well, but a bit higher again than training. This is not always happening, okay? But very good accuracy on mapping rice. If we run this model further, we may get a better accuracy. And I did this. I ran up to about 400 epochs, and I saved the weight on this folder. You'll find it with the dataset as well. So we after running 385 epochs, we got up to 93.11 on validation accuracy. So it improved a lot from the first 15 that we got 75. All right. So if the Colab code was working, sorry again about that, you would be able to run this exact same example on the Colab. I think if we make the model in Python, it should probably work, because I think it's something with the R kernel in the Colab. But well, this is what we have now. So for the prediction, now I have a model. Okay, what do I do with it? I can apply my model with this 93% accuracy onto the whole image. All right, and how do we do that? Well, we have to do the same procedure as the training, in the way that we need to crop, to clip the image into patches again. For the prediction, we don't need to use 128 size. We can increase it a bit so it's a bit faster. So usually we use 512. Let's see what's inside here. Yeah, 512. You see here the block size. So I create first this block size of 512 for the image again. Should plot on the screen soon. If you we have any questions, we can go and answering because it's about time. Have any questions, Veraldo?
Yes. Actually, there are some questions. I will add
Shoot.
Raul so we can share actually, or
Yes.
even Daniel. So Daniel can make the first one that is actually from, let me check, Guilherme Brachiroli.
Guilherme asked, is deep learning methods useful to predict continuous variables like forest above ground biomass? And how to do the sampling, the patches in this case, given that we don't have a class or an object?
Yeah, thank you, Daniel, for the question. This is something, this is a question I already got on the previous conversation with people as well. I think the deep learning applications right now, they are more useful toward classification, image segmentation, and less towards regression. Because of the thing you said, the sampling. I would expect that if you have, for example, for a given image, you have this area is a forest, and you have like the pixels here. How do you get the reference data for the biomass inside each of these pixels? It's very hard. But if you have, for example, a data set of lidar, you could have this information for with airborne lidar, actually airborne lidar. You could get this information for every pixel from lidar, and maybe build a model to predict it with the satellite here, satellite. So I think this is one way to do it. But other than that, the regression problems are kind of hard to predict, like productivity and this kind of stuff. I didn't see many papers doing that.
Okay, cool. Let me see if we have more. David asked, could I provide a CNN many training patches in which I label how many targets are in training patch and then ask the final CNN to count the number of targets in an independent image?
Yes, that's our goal, right? We want to train with a limited number of samples and labels, like a few hundreds, perhaps a few thousands, and then apply to a different area that we do not know the labels, and that it will label it for us. That's a goal.
Okay. I think that is it about questions.
Okay, right. Okay, so going back, I'll try to move a bit faster because we're about to end time here. So this is just an example of the grid with 500 by 500. So they're quite bigger patches in the image. So we do the same procedure in this 7A section. We crop the original image, but now we do it for all these big patches. I think, let me see if I already have this done. It will be a bit faster. Just a second. 300. Yeah, it's the same procedure. I'll not show it on the fly, but it's the same procedure. But this time we don't have the labels, right? We just have the image. So it will look something like this thing. This is a 500 by 500 image. You know, it's the same procedure as before. We crop the images. So that's 7A, and then for 7B we apply the model now to map, to get the labels now for us for this area. So we use the model, and we predict with the model. We predict with the model for the rest of the data set. It's getting some weird red messages. I hope it does not fail for me live. Usually that's when shit happens. But some of these red messages, they're just warnings. So they're just not errors. So sometimes you don't need to be scary with them. I don't remember how long does it take to predict. If it's take much longer, probably skip it right now. Let me see. For this data set, 342. Let me see some 342. I should be fast. Yeah, it already ended. It took 46 seconds, okay, to predict for the all the patches. And to crop at these big patches, it does not take very long as well. It's quite fast. So like I would say 2 minutes, you crop the image and apply the model. It's quite fast. So after we apply the model, the result of the model is still in this pareds object, which has the probabilities for each pixel. All right. So if we see like dimension of threads, it's a bit higher patch size. Not explained here, but we have the borders here. But it's the probabilities. What we do here is on 7C, we recreate the image, like recreate the image tiles with the probabilities, but now we assign a value of 0 or 1 depending on the probability value. If it's less than 0.5, we put 0. If it's otherwise, we put 1. So I will not run this here because the results obviously to create the original images. It will be like let's say it will just create a bunch of images. It's like one image for each patch. It's all black because of the contrast. Don't worry about that. And then we run a mosaic of all these imageries, all these predictions on the output folder to the mosaic folder. And after we run this is quite fast as well. We'll have the result. So just go and show the result for the UNet and also for the random forest from last week. Let me put this. Oh, it's already on the. Oh, okay, I already loaded this. Loaded the data set, the maps. Yeah, it's actually section 8. Sorry, we plot on the screen, bigger screen of RF and UNet. So these two data sets are using the same inputs. The UNet was trained with the patches. The random forest was trained with pixels, one random pixel inside each patch, each field. This is from last week. So we see the UNet and the random forest. You can see that using this single image, the UNet was able to provide a much cleaner result. If you see on the random forest around here, you don't see it here. Right here, you don't see it right here. These are rivers and vegetation that grow nearby these rivers. So these are being confused with rice by the random forest, but not for the UNet. The UNet's doing a much better job with that. And that's mostly because the UNet is looking for the context and the texture within the image patches instead of looking only for the pixel value. All right. So this is like the main takeaway. You get more beautiful, better maps with UNet than you get with random forest for these kinds of applications. And before I end here, I think I have the one measure of accuracy. Let's see if I have this here. I'll just run this section 9 here. I don't recall if this is very long. Yeah, this should be a bit long. Sorry, I will not be able to run this. But in this section 9, if you get the data set, you'll be able to run this and see the accuracy metrics, everything, and compare them, the maps, and see that the UNet performed much better on our application. Okay, so it's already time. If we have more questions, we can stay maybe some minutes past time.
Yeah, Veraldo?
Yeah, actually there is one, maybe Raul can read it.
Are commission errors less likely with the neural net when compared to RF?
Sorry, I didn't understand. He asked, or she asked, what's commission error?
No, if commission's errors are more or less likely with neural networks when compared to random forest.
Well, we expect much less. You see on that example that the vegetation nearby the rivers, they were not rice. Sorry, I didn't plot the few data set on top, so you just have to trust me. But they're not rice; they're vegetation nearby the rivers. The random forest picked those up as rice because the greenness, the near infrared was very high. Let's say it was very similar to a rice field in the spectral signal. But when we look to the context, to the texture, the UNet was able to pick and make a difference out of that. So commission error should be less with UNet. Anything else?
Actually, I think that was the last one.
All right.
Okay. Fernando, I don't know if you want to say the closing words, but before you do that, I just want to thank again Ricardo Alagnon for sharing his experience with us. I am perfectly aware that it was not these lecture times, 6 hours in total. It was also the time that we spent preparing this material. I think it was a lot of time, and well, I can only say that we appreciate a lot. And I hope that we can interact in different ways in the future, not only this way, but maybe in some other forms of cooperation. So thank you very much for that. I think we run out of time, okay? And so from my side, that's all. And I give the word back to Veraldo.
Perfect. Let me just make a announcement. Let me check if the screen is shared. Can you see the screen?
No.
Not yet.
Wait.
Yeah.
Now it should work.
Yes.
Can you see it now?
Yes.
Yes.
Yeah, just a reminder actually for next week, the very on Tuesday, we will have a webinar with Margaret Maiden from the University of Georgia. And with talk, the geospatial analysis to mitigate the human-elephant conflict in Southern Africa. And on Thursday, mathematical morphology and processing and analysis of digital elevation models with Daya Saga from the Indian Statistical Institute, Bangalore in India. So please, if you feel interested in those topics, please register and attend actually the event. Both will be broadcasted, so you can watch and register actually for free. And those are the activities actually for next week. And then for coming weeks, there are actually more talks. So please stay tuned in our program. So I would like to pass actually to Danielle to make also the final words actually, and then we can close actually this tutorial.
Okay, I want to thank you, Ricardo, again for the talk. Very dense for only 3 hours. I think we can stay all day here listening to learn how to run those deep learnings. And I will sure dive deep in the content of the course this afternoon to to understand better. Thank you, Veraldo, for the invitation to be here, and everyone who stay with us all the entire talk.
Perfect. So Raul, if you have the final words, actually, we can
No, I
then
think
close actually.
yeah, I said also my
Yes.
final word. I think that's all. Thank you very much again, Ricardo, and also Veraldo. I forgot to mention the Brazil chapter. It was a kind of joint initiative of the PUC Rio and the Brazilian chapter. It's wonderful to interact with you guys.
Perfect. So we then close actually these tutorials, and the event is then waiting for your participation then in the forthcoming activities. So bye-bye.
Bye.
Thank you very much. Bye bye.
Bye, Ricardo.